Okay, everyone, since we finished the law of sine yesterday, today we're exploring the law of cosine. Ready?
Not really. I always mix up with the Pythagorean theorem.
Actually, that's a good starting point. The law of cosine is kind of like a generalized Pythagorean theorem for any triangle, not just triangle.
Yeah, that's true. In right triangle, the Pythagorean theorem works because one angle is 90 degrees, but for non-right triangles, we need something more flexible. That's where the law of cosine comes in.
Right, so let's write it down first. The law of cosine states c squared equals a squared plus b squared equals 2ab cosine gamma, where a, b, and c are the sides of the triangle and c is the angle opposite side gamma.
Exactly. And notice if C is 90 degrees, cosine 90 degree is 0. So the formula becomes just C squared equals A squared plus B squared, which is Pythagorean theorem.
That's so cool. So basically, the law of cosine covers all types of triangles, not just the right angled ones.
That's correct. Now, when we do you use the law of cosine?
We use it when we know both sides and the included angles as case, and want to find the third side. We know all the three sides is SSK and want to find an angle.
Right. Law of sines works when you know angles and sides nicely paired. But if you only know sides or you have an included angle, you need law of cosine.
Okay, enough theory. Let's do a simple example. Suppose we have a triangle where A equals 5, B equals 7, and C equals 60 degrees. Find side C.
Alright, step by step. Write down the law of cosine, which is c squared equals a squared plus b squared minus 2ab cosine gamma. Substitute the values. We have c squared equals 5 squared plus 7 squared minus 2 times 5 times 7 cosine 60. Simplify, we have c squared equals 25 plus 47 minus 70 times cosine of 60. We know cosine of 60 is 0.5. So c squared equals 25 plus 49 minus 70 times 0.5. So c squared is equals 74 minus 35. We have c squared equals 39. Thus, c equals the square root of 39 is approximate of 6.24.
Nice. So, side C is about 6.24 units long.
Notice how important it is to substitute accurately, especially with cosine values.
Yeah. Also, always double check your calculator. Degrees mode, not region.
Okay, now what about using the law of cosine to find an angle if all three sides are known?
Good idea. Let's try it. Suppose a is equal to 6, b is equal to 8, and c is equal to 10. Let's find the angle gamma. First, rearrange the law of cosine to solve for cosine gamma. Starting with c squared equals a squared plus b squared minus 2ab cosine gamma. Rearranging 2ab cosine gamma equals a squared plus b squared minus c squared. So, cosine gamma is equals a squared plus b squared minus c squared over 2ab.
Substitute the values cosine gamma equals 6 squared plus 8 squared minus 10 squared over 2 times 6 times 8. Simplify. Cosine gamma is equals to 36 plus 64 minus 100 over 96. Cosine gamma equals 0 over 96. Cosine gamma equals 0. Thus, C equals inverse cosine 0. Using the calculator, C is equals to 90 degrees.
That makes sense. A triangle with sides C, A, and also 10 is a classic right triangle.
Right. It matches the Pythagorean triple.
So in this case, law of cosine confirmed that the triangle was right angle.
Exactly. That shows how law of cosine works for any triangle. But when it's right angled, you just get a cosine of 0.
Let's summarize the procedure in solving triangles with law of cosines.
So identify whether you're solving for a side SAS or an angle SSS.
2. Use the proper law of cosine formula.
Step 3. Carefully substitute known values.
Step 4. Solve for the unknown.
And the last step, double check mode, specifically degrees, and double check your final answer if it's reasonable.
Remember, after finding a side or angle, you can sometimes switch to law of sines to find the rest more easily.
That's a pro tip. Law of cosines for the top first part, then law of sines to finish quickly.
Let's do a full application problem to wrap up.
Sure. How about this? In triangle XYZ, side x is equal to 12 cm, side y is equal to 15 cm, and included angle x is equal to 120 degrees. So we have to find the side C.
Alright, start with the law of cosine. Z squared equals x squared plus y squared minus 2xy cosine z. Substitute z squared equals 12 squared plus 15 squared minus 2 times 12 times 15 cosine 120 degree. Simplify z squared equals 144 plus 225 minus 2 times 15 times 12 cosine 120 degree. First, cosine 120 degree is 0.5 because 120 degrees is in the second quadrant where cosine is negative. Thus, z squared equals 144 plus 225 minus 2 times 12 times 15 times negative 0.5. Simplify further. First, calculate 2 times 12 times 15 times negative 0.5 times 2 times 12 times 15 equals 360, and 360 times negative 0.5 is equals to negative 180. Thus, z squared equals 144 plus 225 minus negative 180 z squared equals 144 plus 225 plus 180 z squared is equals to 549. Finally, z squared is equals to root 549, approximate 23.43 centimeter.
Awesome! So side Z is approximately 23.43 centimeters.
Notice how the negative cosine turned into adding. That's very important. Mistakes often happen when you miss the negative sign.
Definitely. Also, we can see that when the included angle is obtuse, the third side becomes the longest side.
Good observation. So for obtuse triangle, law of cosine is super helpful.
Before we end, last common mistake with the law of cosines. Forgetting the negative 2ab cosine gamma part. Wrong substitution, especially with cosine of obtuse angles, forgetting parentheses when entering into calculator, now switching to law of sines when needed to finish solving. Calculator in radians mode instead of degrees.
True. Parentheses really matter because without them, the calculator will do word operations.
Here's a quick tip. If the side you find seems impossible, like a negative length or angle over 180 degrees, double check your computation.
Great discussion. I feel like now law of cosine is way clearer.
Same here. It's actually logical if you break it down slowly.
Agreed. Let's keep practicing more problems later, so we will master it.
Quiz. Here we come.
Let's conquer triangles, one cosine at a time.
Ha ha ha!